Speed and position control of a DC motor. Servo mechanisms are probably the most frequently encountered electromechanical control system. Applications include robots, numerical control machines, and laser printers, to name but a few. We will talk about now DC motor control system, speed response, and effect of the inductance and disturbance to the open loop system. Okay, consider the DC motor control system as we saw before. Okay, this is the block diagram of a DC motor speed control system. How can we get the transfer function of this system? We can use the superposition method. As you know, omega ms can be omega ms for TL0 plus with omega ms for EA is 0. This is the superposition theorem, as you know. First of all, we can get TL is 0. Maybe we can write omega m1, omega m2. Let's get the omega m1 now. Yes, from this diagram, as you see, we can get directly Ki over S square LA Jm plus RA Jm plus Bm LA S plus KB Ki RA Bm. This is the omega m1. What is the omega m2 for EA is 0? How can we draw the block diagram for EA is 0? Let's do this now. We have an input which is TL and with minus, as you see. We have a comparator here and we have a feedback. What is the forward path? 1 over Jms plus Bm. 1 over Jms plus Bm. And the output will be directly omega ms. Omega ms. And we have a feedback here. Feedback consisted of Kb times Ki over by LAS plus RA. Kb times Ki over by LAS plus RA. What is the feedback sign? We have a negative sign here, a positive sign here. If you multiply both of them, you will get minus. So we have minus. So for this system, we can write theta ms over TLS. Sorry about this. In here we have also, maybe we can write as like that. Theta m1s over by EAS. Theta m2s over TLS will be minus, of course, because of the input signal here. Forward path 1 over Jms plus Bm over by 1 plus KB KI over by LAS plus RA times 1 over GMS plus BM. Yes. Finally, we get LAS plus RA divided by S square JM LAS square plus RA JM BM LAS plus RA BM plus KI KB. Yes, this is the another part of the theta m, omega m, sorry. So the final omega m we can get directly as, and we can use this one times with EAS, and then minus times with TLS. Okay, this is the final equation for the DC motor speed system. Okay, let's evaluate the electrical circuit. Let's remember the electrical circuit of the DC motor controls, DC motor system. We have a resistor and inductance, and then electromotive force here. That's all. RA and LA. We here EA and EB. For this system, what is the time constant? Electrical time constant. As you know from the circuit theory, it will be LA over RA. Okay. Okay, for this equation, maybe we can get the time constant of the system. How? The higher order component will be obtained according to the electrical time constant. To do this, maybe we can divide this part with RA and JM. Okay, so all part should be divided by the same equivalent RAJM divided by RAJM and RAJM. So what we have now, Tm will be equal to Ki over JM divided by LA RAS square plus 1 plus BM LA divided by RAJM S plus RABM plus KIKB over RAJM. Okay, what we have now, what is mean? Minus, we have also TL part, as you know, LAS plus RA divided by RAJM Jm divided by the same denominator. TLS, we have here EAS. Okay, this is the final equivalent now. What does it mean? The ratio LA over RA is called the motor electric time constant, which makes the system speed response transfer function second order, as you see. As you see here, if we don't have LA over RA term, so the system will be first order system. Okay? And for the mechanical system, we know this. Electrical time constant is so small with respect to the mechanical system. Okay? So we can easily neglect it or this part. Or maybe you can think about this. LA is the inductance value in the armature circuit, and it is so small value. Okay, so tau E, which is LA over RA, can be accepted as approximately 0. Okay, if we consider this condition, this system will be first order system. Okay, as you see here, the higher order component will be dismissed now. Let's do this. TMS will be equal to Ki over RAGM over by S plus Ki KB plus RA BM over by RA JM. This is the first part, EAS. As you see here, in here we have also LA over RA part. So this term will be accepted as 0. We get S value from here. Okay, the remaining part, as you see. Let's continue from moment 1 over Jm over by S plus Ki KB plus RA BM divided by RA Jm times with TLS. Okay, we can express this equation also. Kf over by tau ms plus 1 EAS and minus tau m over Jm divided by tau ms plus 1 times with TLS. Okay, what is the Kf? As you see here, we have another new constant. Kf is Ki over RABM plus Ki KB. And tau m, this is the mechanical motor constant. It will be RAJM divided by Ki KB plus RABM. Okay, now we have a standard first order system, so we can easily evaluate this system now. If we take the Laplace transform for the last equation and talk about this equation, if we take the Laplace transform regarding the TL as 0, TL is equal to 0, and EA is equal to A. It means EAS will be A over S. Okay, if we take the inverse Laplace transform of the omega m, we will get A times Ki over by Ki times Kb plus Ra times Bm times with 1 minus e to power o minus t over tau m. What does it mean for us? In this case, we have to remember time constant, mechanical time constant. Motor mechanical time constant is reflective of how fast the motor is capable of overcoming its inertia. Inertia is Jm, as you know. For what? To reach the steady state value of the speed. What is the final value for the system? Final value of rotational speed will be equal to A times Ki over Ki times Kb plus Ra times Bm. This is the final value of the speed. For the mechanical motor constant, we can say is the tau m. If the tau m is increased, we can say the system is slow, or vice versa. If we consider TL as d, it means TLS will be d over s. And input is the same as A over S. We can get the time domain equation now. Ki over Ki times Kb plus Rabm times with A minus Rad over Kb times with 1 minus e to power o minus t over tau m. Okay, this is the time response of the speed. So what is the effect of the load moment now? We'll talk about it. If we take TL as 0, we get this equation. If we take TL as D, we get this equation. What is the difference between them? Let's look at now. As we see here, we have a new term here, which is given as minus Ra times T over Ki Kb times with Ki over Ki Kb plus Ra Bm. So we can say directly the final value of rotational speed with the load moment will be equal to Ki over Ki Kb plus Ra Bm times with A minus Rad divided by Ki Kb. So the new final value, as you see, load moment affect the system with this term. What is mean? If we draw the speed, rotational speed, with respect to the t, with the reference value, the system will behave as like that if we don't have a load or no load. But if we have a load moment, the system will behave as like that with the load. This difference can be explained with this equation. System will not go to the reference value with the load value. What does the tau mean? Tau is this point, this is assuming, so the final value is 63.2%. This is the mechanical time constant. So with the effect of the load, system will not go to the reference value. Please remember that we are talking about open loop system now. We don't have a controller. We are talking about the open loop system. Also, I have to say this, the value of the torque moment may never exceed the motor stall torque. The value of TL in this condition given as D may never exceed the motor stall torque. How can we express it in mathematically? We can use this equation A minus RAD over Ki times Kb should be greater than 0. How it is possible? A Ki Kb over Ra should be greater than D. How can we get the stall torque value? The value of the stall torque can be obtained by the manufacturer catalogs. Now we are going to talk about a closed loop system. The output speed of the motor is highly depending on the value of torque. As you see before, we can improve the speed performance of the motor by using the proportional feedback controller. Controller is composed of a sensor and amplifier gain. Maybe we can easily understand from the block diagram. We have an input value, comparator, a proportional controller, and then we get EA here. Here we have EB, Ki over by LA, S plus RA. We have load torque here, and then 1 over JMS plus PM, and we have output here, omega M, and we have a feedback here with the gain of Kb, so we get EB. Now the closed loop system will need also a sensor here with the gain of Kt. Then we have actual rotational speed of this motor. This is the closed loop system of the DC motor speed control. Note that the speed of the motor shaft is sensed by a tachogenerator or tachometer with a gain Kt, as you see. Actually, for this system, we have already know the transfer function of this part. We have already know this part, so we have a gain here and a feedback here. What is the final equivalent of the transfer function? After the sum arranging, we get kt times ki times k divided by rajm over by s plus ki kb plus rabm plus kt ki k over by rajm. This is the first part of the equivalent of the speed. Sorry, here we have input as omega in. If we use uppercase, it will be as like that. Minus with the load torque part, 1 over Jm divided by S plus Ki Kb plus Rabm plus Kt Ki K divided by Rajm with the load torque. If we apply a step input again, omega in will be applied as A over S, and TL is D over S. So the time response of the system after the inverse Laplace, we get omega m will be equal to A times K times Ki times Kt divided by Rajm times with tau times with 1 minus e to power of t over tau minus tau times d divided by Jm 1 minus e to power of t over tau. This is the time response of the system. What is the tau value? Tau can be given as Rajm over by Ki Kb plus Rab plus with Kt Ki K. Okay. What is the steady state response? We can get easily. Final value of it will be A times K, Ki, Kt divided by Ki, Kb, Rab plus Kt, Ki, K minus Rad over Ki Kb plus Rabm plus Ki Kt K. This is the final value of the speed. Okay, what does it mean? What is the effect of the controller to the system? As you see here, this part is about the load moment. This part is about the input of the system, which is EA. What is the proportional gain for this system? Here, as you see, it is controller, proportional control. It is given with K. Where is it here? As you see here, it is the denominator part of the load moment. So, what does it mean for us? The controller gain can reduce the effect of the disturbance because high K values, the disturbance effect can be reduced. By increasing the K value, we can reduce the effect of this part. So, load torque effect can be reduced. Of course, we have some limitation here, such as amplifier saturation, motor's input voltage, or as like that. Let's continue from the position control now. The position response of the open loop case may be obtained by the integrate of the speed response. If we integrate of the speed control system, we can get position control. We get already open loop system here. We can use this equation for the position control by integrating it. This is the speed control system. But we know this omega mt is equal to d theta t, theta mt over dt. So it's mean omega ms will be equal to s times theta ms. Okay. By using this equation in the first equation, theta ms over EAS will be equal to Ki over S times S square LAJM plus blah blah. Okay, this is the position control system. Okay, for this system, if we evaluate TL as 0 and BM is 0, and if we take inverse Laplace of it, we can get directly theta mt will be equal to A over KB times T plus tau m e to power of minus T over tau m minus tau m. This is the time response of the position control. For this system, what is the block diagram? Theta in with controller K. So we get EA. We have a comparator here, plus and minus. We continue from Ki over LAS plus RA. Here we have a torque value 1 over JMS plus BM. Now here we have omega value, and we need also an integrator here to get the theta m. In here we have a feedback KB, and then we need also to sense the output to control the system with the gain with Ks. This is the actual position value. Okay. If you do a needed operation here, you will get theta m s over theta in. This is the reference value. You will get finally Ki, Ks over Ra divided by, maybe we can express it again, tau ES, which is electrical constant of the system, Js square plus Bm plus Kb Ki divided by Ra S plus K Ki Ks over by Ra. In here again we can neglect the electrical time constant again, which is La over Ra assumed as 0 again. So the system will be equal to 1 over Ks times K, Ki, Ks divided by Raj divided S square plus Rabm plus Kb divided by Raj, which is S. And then we continue K, Ki, Ks over by Raj. As you see here, this is the second order prototype system. This is similar with this omega n square divided by s square 2 kc omega ns plus omega n square with the gain 1 over ks here. Okay, so we can do a control for this system, which is done before in the chapter 3. Okay, as a result, for a step input we can directly control the position of the DC motor, because this is the second order prototype system. We can do the control operation on the system. How? As you see here, Ks is the gain of the sensor, feedback sensor here, and we have a proportional control gain, which is K. So with using the proper K value, you can easily control the position of the DC motor. Okay, that's all.